In the beginning, the universe appeared as a perfect equation, a tapestry of forces and particles balanced in exquisite symmetry. Every electron paired with its charge, every quark bound by unseen strings of force, every photon racing outward, to carry light across the abyss to the eye of reason. It was flawless, a cathedral of mathematics where nature obeyed its own harmony. But within the silence of this order came a whisper, a disturbance in the data, a trace so faint it might have been illusion, yet so persistent it could not be ignored. A ghost moving where no presence should exist, a particle that defied the architecture of physics itself. Nature was supposed to be elegant, self-consistent, yet here, in the flicker of an anomaly, was something that should not be. Like a single misplaced stone in a cathedral's arch, its existence threatened collapse, a contradiction so profound it could unravel the structure of the cosmos. Scientists leaned closer, uncertain. If it was real, it would mean the laws written across a century of discovery were incomplete. If it was not, then why did reality continue to whisper its presence in every corner where shadows of uncertainty gathered? This is the paradox, a particle that should not exist. It is not only a question of physics, but of existence itself. If true, it reveals that the universe is deeper, stranger, and far less stable than the equations we trust. If false, it leaves a haunting echo, a reminder that even silence can conceal storms. At the heart of modern science lies this riddle, the search for the impossible particle, the one that should not exist. The story of the impossible particle does not begin in the modern age of colliders and satellites. It begins in an era when the atom itself was still a dream, when scientists argued not about quarks or bosons, but about whether matter could even be divided into pieces too small to see. In the closing years of the 19th century, a series of discoveries reshaped everything. In 1897, J.J. Thomson uncovered the electron, the first subatomic particle to step out of invisibility. It was tiny, charged and universal, a fragment of matter smaller than any philosopher had dared imagine. The electron was the opening of a new door. Beyond it, the microcosm was waiting. In the decades that followed, Planck measured the spectrum of light and found discreteness where there should have been continuity. Einstein declared that light itself was made of quanta, packets of energy that could strike metal like stones on glass. Bohr described the atom as a solar system in miniature, with electrons orbiting a nucleus of dense protons and neutrons. And then came de Broglie, whispering that particles were not merely particles. They were waves, spread, uncertain, shifting, between being and not being. Schrödinger carved this vision into mathematics. His wave equation described electrons not as dots, but as probabilities, smeared like mist around the heart of an atom. Heisenberg carried the idea further. His uncertainty principle declared that nature itself imposed limits on knowledge. The more precisely one knew a particle's position, the less one could know its momentum. Certainty had died. Probability reigned. The dawn of quantum mechanics was both triumphant and unsettling. For the first time, scientists glimpsed the scaffolding of reality, yet within the triumph lay hints of unease. A world built from waves of probability was strange enough, but stranger things were waiting by the mid-20th century. Machines had been built to rip open the atom and peer into its hidden heart. Particle accelerators, vast rings of magnets and chambers, became the new cathedrals of science. They flung protons together at near-light speed. And when the collisions came, nature revealed its secrets, in showers of fragments. Here emerged the zoo of particles, muons, pions, kaons, baryons, mesons, a bewildering bestiary of fleeting entities that existed for mere instants before dissolving. The universe, it seemed, was far messier than once imagined. Yet hidden within the chaos was a structure waiting to be found in time. Physicists assembled the Standard Model, a framework of quarks and leptons bound by forces carried by bosons. It was a portrait of elegance, the strong nuclear force welding quarks into protons and neutrons, the weak force guiding radioactive decay, electromagnetism binding electrons to nuclei, and gravity still lingering apart. Unsolved. The Standard Model predicted with uncanny accuracy. Particles that had not yet been seen were found exactly where the equations said they would be. The W and Z bosons emerged at CERN in the 1980s. The Higgs boson, the long-predicted giver of mass, was finally uncovered in 2012. For many, it seemed, the story was complete. Physics had achieved its cathedral, but anomalies whispered in the corners of the data. The first came from the Sun. In the 1960s, detectors buried deep underground began to catch ghost-like particles streaming from nuclear reactions at the Sun's core. These neutrinos were supposed to arrive in predictable numbers, yet experiment after experiment found only a fraction of what theory demanded. The Sun, it seemed, was lying, or perhaps something deeper was at play. For decades, this solar neutrino problem haunted physics. Then came the revelation: neutrinos were not static identities. They could oscillate, changing from one type to another as they traveled. This meant something extraordinary. Neutrinos had mass, however slight, even though the Standard Model declared them massless. The equations of physics had not just been bent, but broken. It was the first confirmed crack in the cathedral. Other hints emerged. In the 1970s, physicists studying cosmic rays discovered the muon, a heavier cousin of the electron. It was stable long enough to measure, and it seemed ordinary until its behavior was tested with exquisite precision. The muon's magnetic moment, the tiny wobble of its internal spin in a magnetic field, was subtly wrong. The measurement did not agree with the prediction. The difference was small parts per billion, but relentless. Something unseen was tugging at the muon. Quantum leash. Decades later, as experiments grew more sensitive, the discrepancy refused to vanish. At Brookhaven National Laboratory, and later at Fermilab, the muon's magnetic anomaly persisted. To explain it, physicists whispered of unknown particles, of hidden forces. Perhaps the muon was sensing a ghost from beyond the Standard Model, and then, in the laboratories of Hungary, another anomaly surfaced. Nuclear transitions of beryllium and helium seemed to release energy in patterns no theory could explain. From the data emerged a tantalizing possibility: a new boson, dubbed X17, carrying a force beyond the four known to science. A fifth force, hidden in plain sight. The whispers grew louder. Meanwhile, the great accelerators, CERNs, Large Hadron Collider, above all, continued to probe deeper, in the wreckage of collisions. They sought not only the Higgs, but the shadows of sterile neutrinos, hypothetical particles even more elusive than their ordinary cousins. These sterile neutrinos would not interact with matter at all, save through gravity. They would be invisible to every detector, and yet, if real, they might explain the invisible mass of the universe, dark matter. Step by step, the narrative took shape. The Standard Model was not wrong, but incomplete. The anomalies were not errors, but signals. the impossible particle, was out there glimpsed in neutrino oscillations, in the muon's defiant wobble, in the strange decay of beryllium nuclei. Each anomaly carried with it the weight of history. For in every era of science, new revolutions began not with certainty, but with whispers. The orbit of Mercury betrayed Newton's law. The photoelectric effect betrayed classical waves of light. And now, the particles themselves betrayed the standard model. What if the impossible particle was not a mistake at all? What if it was the next doorway? The stage was set. At the heart of the story lay the growing conviction that nature was hinting at something new, something hidden, a ghost, particle that should not exist, and yet might. For nearly half a century, the standard model reigned as one of the most triumphant achievements in science. Its equations, elegant in their symmetry, predicted a universe of particles and forces with astonishing precision. It accounted for the quarks that built protons and neutrons, the leptons that carried charge in mass, and the bosons that mediated the fundamental interactions of nature. Every discovery, from the W and Z bosons in the 1980s to the Higgs boson in 2012, had seemed to confirm its power, and yet, hidden beneath this triumph, lay a gathering unease. For the universe did not seem content to obey the model's perfection. One by one, small cracks began to appear, each threatening to undermine the entire cathedral of physics. The first shock had come with neutrinos. According to the standard model, these ghost-like particles should have no mass. They should be pure messengers of the weak force, streaming from the sun in fixed numbers, unchanged by the journey. Yet the solar neutrino problem refused to vanish. Neutrinos arriving on Earth appeared to change their very identities in flight, a transformation known as oscillation. Such oscillation was possible only if neutrinos possessed mass. The violation was subtle but devastating. One of the standard model's fundamental assumptions had been broken. This was more than a footnote in physics. Mass, in quantum theory, is not simply a number. It is the bridge between symmetry and reality. The Higgs field had been invoked precisely to explain why particles had mass at all. If neutrinos defied this framework, then either the Higgs mechanism was incomplete or an entirely new principle was at work. The universe was whispering that the model, though beautiful, was not the final word. Then came the muon, a heavier cousin of the electron. It seemed at first to be nothing more than an afterthought in nature's design. But when physicists measured its magnetic moment, the infinitesimal precession of its spin in a magnetic field, they found something unsettling. The muon wobbled more than the equations allowed. The deviation was small, measured in parts per billion. But the standard model prided itself on such precision. To miss by even this fraction was not a trivial flaw, it was a betrayal. Either the experiments were mistaken, or something invisible was tugging at the muon, an unseen particle or force altering its dance dot. At Brookhaven National Laboratory in the late 1990s, the anomaly first sharpened into focus. Later, at Fermilab, the discrepancy persisted with even greater confidence. It was as if the muon, by its silent spin, was pointing toward a new physics. The shock deepened. The anomaly was too consistent to dismiss, yet too radical to accept, without caution. And then came perhaps the most startling claim of all. In Hungary, nuclear physicists studying the decay of beryllium nuclei observed a strange excess of electrons emitted at peculiar angles. The data resisted conventional explanation. From their analysis emerged the proposal of a new boson, a particle-carrying force, but of a kind unknown to the four already enshrined: gravity, electromagnetism, the strong and the weak. This new boson, dubbed X-17, seemed to whisper of a fifth force of nature. The implications were staggering. For centuries, physics had been defined by its ability to unify forces. Newton bound falling apples with orbiting planets. Maxwell united electricity with magnetism. Einstein connected gravity with the fabric of space-time. If X-17 were real, it would mean that the unity was not complete. A hidden interaction, unknown for all of human history, might still be shaping the cosmos. The shockwaves rippled through the scientific community. Was this another illusion, a statistical fluke waiting to vanish under closer scrutiny? Or was it the first glimpse of a new chapter in physics, a particle that should not exist within the old laws, yet undeniably hinted at its presence? The emotional weight of these anomalies was profound. For generations, stars had been taken as symbols of permanence, electrons as anchors of matter, the standard model as the completed map of reality. To see these anchors shaken was to confront a new kind of fragility. The universe itself appeared less stable, less knowable than once imagined. The philosophical dread grew sharper still when scientists contemplated the consequences. If sterile neutrinos existed, then the balance of cosmic matter might be rewritten. If the muon anomaly proved real, it could signal entire families of undiscovered particles. If X-17 existed, the fabric of reality might contain an extra thread, weaving an interaction more subtle than any ever known. But what most unsettled physicists was the possibility that the anomalies pointed not toward a single new discovery, but toward the collapse of an entire worldview. The standard model was not just a theory. It was the very grammar of physics. To break it was to risk unraveling the sentences by which reality was described. This was the scientific shock, the realization that the particle which should not exist might in fact be real, and if so, it would demand a rewriting of physics as profound as the revolutions of relativity or quantum mechanics. The cathedral of modern science, so carefully built across the 20th century, trembled at the possibility of a single misplaced stone. And yet, as always, science did not retreat, for in every paradox lay the promise of revelation. The shock of anomalies in physics was not the end of the story. It was the beginning of a pursuit that spanned the globe, drawing humanity's most advanced instruments into the search for a whisper, the faint trace of a particle that should not exist. The first frontier was neutrinos. Ghost-like, they streamed endlessly from the heart of stars, passing through entire planets as if matter were transparent. Billions traversed every square centimeter of Earth each second, yet almost none left a trace. To catch them, physicists built cathedrals of silence, deep in the Kamioka mines of Japan. The Super Kamiokande detector was filled with 50,000 tons of pure water. Surrounding it were thousands of photomultiplier tubes, waiting to detect the faintest flash of blue Cherenkov light, the rare signal of a neutrino colliding with an atom. In Antarctica, the Ice Cube Observatory extended this search into the very ice itself, transforming a cubic kilometer of frozen darkness into a listening device for neutrinos arriving from the most violent corners of the cosmos. It was in these silent halls that the mystery of oscillation became undeniable. Neutrinos shifted identities as they traveled, from electron neutrinos to muon neutrinos to tau neutrinos. This metamorphosis implied mass, and if neutrinos had mass, they had broken. one of the sacred symmetries of the standard model. The deeper the detectors looked, the stranger the puzzle became. Some experiments hinted at sterile neutrinos that did not interact through the known forces at all, slipping even more deeply into invisibility. To confirm their existence would be to admit that the cosmos was filled with a shadow. Population of particles, possibly as abundant as the visible universe itself. Perhaps the very essence of dark matter. The second frontier lay in the moon. At Fermilab in Illinois, the Muon G2 experiment stored trillions of these particles in a perfectly circular ring, their spins precessing like gyroscopes in a magnetic field. Each turn of the muon revealed a discrepancy, a stubborn deviation, from the predictions of the standard model. The precision of the experiment reached into billions. Yet still, the muon refused to conform. Was the anomaly a window into undiscovered forces? Or was it a flaw in the theoretical calculations themselves, buried in the complexity of virtual particles and quantum loops? Teams of physicists around the world refined the mathematics, pushing computers to their limits to calculate the quantum froth of the vacuum. Yet the gap remained, as if some unseen hand were nudging the muon's dance. The third frontier emerged in nuclear physics, where researchers studied the subtle behavior of atomic transitions. In Hungary, an experiment with beryllium nuclei revealed an unexpected excess, electrons emitted at angles no model predicted. The simplest explanation was almost unthinkable: a new boson, carrying a fifth force of nature, mediating interactions that had escaped all previous detection. They called it X17. Other groups attempted replication. Some found hints, others silence. The anomaly lingered in uncertainty, suspended between revelation and illusion, but its possibility haunted the field. If true, it would be the first addition to the fundamental forces since the early 20th century. It would demand not just revision, but revolution. And so the investigation spread beyond laboratories to the cosmos itself. For the universe to parse, a vast experiment unfolding across billions of years. The cosmic microwave background, mapped by satellites like COBE, WMAP, and Planck, revealed the afterglow of the Big Bang in exquisite detail. Within its patterns, scientists found constraints on the number of neutrino species, the sum of their masses, and the role they played in cosmic evolution. The data hinted at a delicate balance, one that sometimes clashed with the lab suggestions of sterile neutrinos. If such particles existed, why did the cosmos not reveal their imprint? Baryon acoustic oscillations, the fossilized sound waves of the primordial plasma, told another story. They mapped how matter clumped under gravity, subtly influenced by the unseen hand of neutrinos. Every survey of galaxies, every ripple frozen into cosmic structure, became a record of the particle storm that had once raged in the young universe. Meanwhile, black holes offered their own laboratory. Near their event horizons, space boiled with quantum fluctuations. Hawking had shown that even the vacuum was alive with storm-like radiation. If sterile neutrinos or hidden bosons existed, they might shape the way black holes evaporated or influence the balance of entropy at the edge of time. Particle physics and cosmology converged, weaving together laboratory precision and cosmic vastness. Yet the deeper the investigation, the greater the tension. Some data suggested hidden particles, others imposed strict limits on their existence. Supercomputers roared into life, simulating quantum field theories and the behavior of particles. In early universe conditions, every calculation carried both hope and unease. Was the universe revealing its secrets? Or was it constructing illusions, leading humanity in circles around a truth it could never fully reach? The frozen silence of dark matter deepened the mystery. For nearly a century, its presence had been inferred only through gravity, pulling galaxies into spirals and binding clusters together. Yet every search for the dark matter particle in liquid xenon chambers, cryogenic detectors, and underground vaults returned with emptiness. Could the particle that should not exist be the hidden face of this darkness? Could sterile neutrinos, or X-17, or some unseen cousin of the muon be the long-sought key? In this stage of investigation, science became a mirror of philosophy. Each experiment was not merely a measurement, but a wager that reality was coherent, that anomalies were not tricks but truths. And yet, with each deeper probe, the cosmos offered more riddles than answers. The investigation had begun with a whisper, a hint of impossibility. Now it had grown into a chorus of contradictions. Neutrinos with mass, muons wobbling into strangeness, bosons that carried forces unknown. The standard model bent beneath their weight. Still, the question remained unresolved. Were these anomalies glimpses of a greater law, or shadows cast by errors and illusions? The search pressed onward, deeper into the storm of reality. For the stakes were no longer limited to particles. What was at risk was the very language of physics, the grammar by which humanity described the universe. If the anomaly was real, the story of matter itself would have to be rewritten. The search for the impossible particle had begun as a ripple, a faint disturbance in the sea of physics. But with time, the ripple became a storm. Every new experiment, every observation seemed to deepen the paradox instead of resolving it. The mystery grew, expanding outward like the universe itself, drawing in not only laboratories, but the very structure of reality. At first, scientists hoped the anomalies would dissolve with precision. Perhaps a miscalibrated instrument, a statistical fluke, or a subtle error in calculation. Yet the anomalies refused to vanish. The neutrino continued to oscillate, slipping between identities with ghost-like defiance. The moin continued to wobble against prediction, as though tugged by an invisible hand. The X-17 anomaly lingered in the shadows of nuclear physics, neither disproven nor confirmed. Like a half-seen figure in the fog, the stakes grew heavier with every failed resolution. If sterile neutrinos existed, then the standard model, the most successful framework in science, was incomplete. Worse, it was misleading. The universe, which had seemed so elegantly ordered, now hinted at hidden layers, secret chambers. Beyond the reach of current equations, the consequences reached into cosmology. If sterile neutrinos or unseen forces existed, they could reshape our understanding of the cosmos itself. Dark matter, that silent scaffolding of galaxies, might be explained not by exotic new physics, but by a particle long suspected yet never caught. The invisible structure of the universe could be built upon. The very thing that should not exist, but contradictions multiplied. Cosmological data from the Planck satellite placed tight limits on the number of neutrino species that could exist, and on their collective mass. If sterile neutrinos were real, why did the early universe not reveal their fingerprints in the cosmic microwave background? Why did the fossil light of the Big Bang seem to contradict the whispers in the detectors buried beneath mountains and ice? This tension between the very large and the very small cut to the heart of physics. Laboratory results suggested something was missing. The cosmos itself suggested otherwise. Which one told the truth? Could both, or was the universe more deceptive than either framework could admit? The possibility of a fifth force of nature raised the stakes even higher. For centuries, physics had known only four: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. To imagine a fifth was to imagine that the very architecture of interaction was incomplete. If the X-17 boson was real, it might weave its influence through matter in ways invisible to past generations, subtly altering nuclear transitions, shaping the cosmos in hidden ways. The elegant cathedral of known forces could collapse beneath the weight of a single misplaced stone. Meanwhile, the Morn anomaly persisted like a wound in theory's side. The discrepancy between prediction and experiment was small, a few parts per billion, yet immense in its significance. For, in physics, precision is destiny. A tiny deviation, measured and confirmed, can open an entire new realm of law. Supersymmetry was one candidate, suggesting that every known particle had a heavier twin, hidden just beyond reach. If so, the muon's defiance was not a mistake, but a signal, a whisper from the shadow world of SUP-ARPARTN, and still the contradictions grew. Cosmologists attempted to reconcile the hints of new physics with the structure of the universe. If sterile neutrinos existed, why did galaxies form as they did? If new bosons mediated unseen forces, why had their effects not yet reshaped the evolution of stars? Each answer dissolved into deeper questions. The escalation was no longer about a single particle. It was about coherence itself. Could the universe still be described by a unified framework? Or had the dream of symmetry, simplicity, and completeness always been an illusion? The philosophical weight became unavoidable. Science had long assumed that anomalies were temporary, that mysteries would vanish beneath deeper understanding. But what if the universe was not a puzzle waiting to be solved, but a labyrinth designed to deceive? What if contradictions were not errors, but features of a deeper order? For every experiment, the question sharpened. Either there was something beyond the standard model, or the data itself was misleading. Both possibilities carried fear. If new physics existed, then humanity stood at the edge of a revolution, a rewriting of reality as profound as quantum mechanics itself. If no new physics existed, then the hints, the whispers, the anomalies were illusions, a reminder that even the best tools of science could be misled by shadows. The image of the impossible particle began to shift. It was no longer a single anomaly. It was a mirror. In its reflection, physics saw both its triumphs and its limits. The standard model explained so much, yet not enough. Gravity remained outside its walls. Dark matter and dark energy hovered unexplained. And now the anomalies pressed harder, as if reality itself were reminding humanity that the story was not finished. Speculations grew bolder. Perhaps the anomalies were not independent. Perhaps the neutrinos, the muon, and the X-17 were fragments of a larger truth, hints of a hidden scepter, a shadow universe of particles and forces that interacted faintly with our own. This hidden world, if real, could account for dark matter, explain cosmic tensions, and reveal why the standard model worked so well, yet left so much unexplained. But with speculation came dread. If such a hidden sector existed, it might be forever. Beyond reach, interacting so faintly that even the largest detectors, the most powerful colliders, could only glimpse its echoes. The universe might be filled with secrets that could never be brought into light. The escalation of the mystery brought physics into crisis. The standard model had been both triumph and prison, binding thought within its walls. Now those walls cracked. But no new structure had yet emerged. The particle that should not exist had become more than anomaly. It had become a symbol of uncertainty, itself dark, and as the search deepened, so too did the realization. To find this particle, to prove or disprove its existence, was not merely to extend physics. It was to confront the very possibility that the universe itself might not be comprehensible. In human terms, in the halls of physics, where chalk drifts across blackboards and supercomputers hum with equations, the mystery of the impossible particle has forced theory into the unknown. When experiment whispers of anomalies, theory responds with visions. Frameworks that stretch beyond the visible architectures of possibility. The most venerable among them is supersymmetry. For decades, it has haunted the dreams of particle physicists. A hidden symmetry suggesting that every known particle, electrons, quarks, photons, has a twin. These twins, heavier and unseen, would complete the tapestry, stabilizing the equations of the standard model, binding the forces into unity. In supersymmetry, the impossible particle is not an intruder but a herald, a faint echo of its unseen partner. If true, supersymmetry could explain why the Higgs boson exists at all, why the universe did not collapse in its infancy, and why dark matter cloaks galaxies in silence. Yet supersymmetry has remained elusive. The Large Hadron Collider, the greatest machine of its kind, was built in part to reveal these shadow twins. But collision after collision, petabytes of data later, the partners remain hidden. The absence deepens the tension. If supersymmetry is real, it must exist at energies higher than expected, perhaps forever beyond our reach. If it is not real, then the anomaly points elsewhere, to stranger truths. Others turn to the ghost-like neutrino, already known to defy expectation. Its mass, its oscillations, its chameleon identity, all whisper of incompleteness. Some propose the existence of sterile neutrinos, particles that interact only through gravity, invisible to detectors save for their subtle fingerprints on oscillations. If real, sterile neutrinos could be the long-sought dark matter, the missing mass of the cosmos. The impossible particle may not be a stranger to the universe, but its hidden scaffolding, holding galaxies in their shapes. Unseen yet essential, still others speak of a more radical possibility, a fifth force of nature. If the X-17 boson exists, then the four known forces are incomplete. A hidden interaction may bind matter in ways subtle yet profound, explaining nuclear transitions that defy prediction, shaping atoms at their core. A fifth force would rewrite textbooks, but more than that, it would imply that the universe has held secrets from humanity since its beginning. The cathedral of physics, once thought complete, would open to new chambers, unexplored and vast. Beyond these, speculation grows bolder still. Some suggest that the anomalies hint not at particles, but at extra dimensions. In such visions, the impossible particle is not a ghost within our universe, but a messenger from another. It appears anomalous because part of its being resides beyond the familiar 3 dimensions of space and one of time. If true, the impossible particle may be the first tangible clue of a multiverse, a layered reality where our cosmos is but one strand in a cosmic web. String theory, too, lingers at the edge of this speculation. In its mathematics, particles are not points but vibrations of tiny strings, their harmonies producing the zoo of matter and forces. The impossible particle, in this view, may be a dissonant note, a vibration we have not yet heard clearly. It may signal that string theory's hidden dimensions, curled tighter than atoms, are not entirely silent, but whispering through anomalies. Another possibility is darker, that the anomalies are false alarms, tricks of statistics, shadows mistaken for substance. Science has faced this before. Ghost particles and phantom signals have haunted laboratories only to fade under scrutiny. Perhaps the impossible particle is not real, yet even here the persistence of anomalies carries meaning. Why does nature allow such whispers? Why does experiment, time and again, brush against the edges of the unknown? The philosophical reach grows heavy. Each theory, supersymmetry, sterile neutrinos, fifth forces, extra dimensions. String theory is not only a scientific attempt, but a reflection of desire, the human longing for unity, for coherence, for deeper order, to accept the impossible. Particle is to accept that reality is larger, stranger, more layered than the standard model ever imagined. To deny it is to admit that even illusions can mislead entire generations of thought. The heart of speculation lies not in certainty, but in possibility. If supersymmetry is true, then the impossible particle is the door to unification, the bridge between the quantum and the cosmic. If sterile neutrinos are real, then the impossible particle is the hidden mass of the universe, the silent architect of galaxies. If the fifth force exists, then the impossible particle is proof that nature's grammar is incomplete. If extra dimensions breathe into reality, then the impossible particle is the first messenger from realms beyond. And yet, in every scenario, one truth remains. The impossible particle changes everything. It redefines what is known, erases the boundaries of the standard model, and reminds humanity that physics is not finished. The equations that carried us from Newton to Einstein, from quantum mechanics to the Higgs boson, are not the final chapter. They are prologue. Speculation becomes a mirror of existence itself. The particle that should not exist is not only a challenge to physics, it is a metaphor for reality, fragile, contradictory, refusing to be contained in perfect symmetry. Perhaps the universe was never meant to be simple. Perhaps its beauty lies not in elegance, but in mystery, in the persistence of anomalies that will not go away, in the laboratories of the present, in the theories of the future. The impossible particle waits, whether as truth or illusion. It is already shaping science, bending thought toward the unknown. It may yet reveal itself as dark matter, as a fifth force, as a ghost from another dimension. Or it may fade into silence, a reminder of the limits of human sight. But for now, speculation remains the storm before discovery. The impossible particle lingers at the edge of knowledge, a riddle without answer, yet rich in meaning. And in its shadow, humanity confronts the possibility that the deepest truths of the universe may lie forever beyond glimpsed, but never fully grasped. In the modern age, humanity has become a builder of instruments vast enough to rival myths. Towers of magnets, oceans of sensors buried beneath mountains, eyes in orbit that never blink, all created to answer a single question: does the impossible particle exist? The search has become not just an act of science, but of devotion, a pilgrimage of technology into the heart of the unknown. The first and most powerful among these temples of inquiry is the Large Hadron Collider LHC at CERN, beneath the fields of Geneva. A 27-kilometer ring of superconducting magnets hurls protons to near light speed, smashing them together with energies once reserved for the birth of the universe. In its collisions, new particles are born, flashes of creation lasting a fraction of a second before decaying into patterns of fragments. It was here that the Higgs boson revealed itself in 2012, a discovery that fulfilled a prediction half a century old. But the LHC continues to search beyond, probing anomalies that whisper of sterile neutrinos, hidden bosons, and supersymmetric partners. Each upgrade sharpens its vision, increasing luminosity to chase signals fainter than starlight. If the particle that should not exist is real, perhaps it will leave its trace in the debris of these collisions, an echo caught in the subatomic storm. Yet the collider is only one frontier. Deep beneath the Japanese Alps lies Super Kamiokande, a cavern filled with 50,000 tons of ultra-pure water. Here, neutrinos, ghost particles that pass through planets as though they were transparent, occasionally collide with atoms, producing a cone of blue Cherenkov light. This vast silence detector has already revealed neutrino oscillations, proving that neutrinos have mass, a discovery that shattered the standard model. Its successor, Hyperkamiokande, now under construction, will extend the search, perhaps capturing the signature of sterile neutrinos, particles that hide from all but the most sensitive of instruments. In the frozen wastes of Antarctica, another detector, IceCube, watches a cubic kilometer of clear ice for faint flashes from neutrinos born in cosmic cataclysms. These observatories form a global net, straining to catch whispers of the impossible. Meanwhile, at Fermilab in the United States, a ring of magnets smaller than the LHC carries a burden of enormous weight, the Moin-G2 experiment. Here, physicists track the magnetic wobble of muons, heavier cousins of the electron. The standard model predicts their motion with exquisite precision, but the experiment has found a deviation, a subtle, persistent difference, hinting that unseen particles or forces tug at the muon's path. If true, the anomaly is one of the clearest signs of physics beyond the standard model. The impossible particle may live in this deviation, hidden in the trembling of a magnetic moment. Other experiments hunt for the elusive directly. In the United States and Europe, liquid xenon detectors like Xenant and Luxaplin sit buried under mountains, shielded from cosmic rays, waiting for the faint touch of dark matter. They are immense vats of noble liquid, capable of sensing a single particle scattering within. If sterile neutrinos or other exotic particles form dark matter, then one day, perhaps, a solitary signal will ripple through these detectors, rewriting physics in an instant. Cosmology too has become a laboratory. Satellites such as WMAP and Planck have mapped the cosmic microwave background, the afterglow of the Big Bang, with precision so fine it rivals a sculptor's hand. These maps constrain the number and properties of neutrinos, hinting at tensions between cosmological predictions and laboratory results. Future missions, like CMBs-4 and Light Bayard, will probe even deeper, searching for primordial ripples that may reveal whether anomalies in particle physics are woven into the earliest fabric of the cosmos. On Earth's surface, telescopes like the Vera Rubin Observatory will chart billions of galaxies, mapping the influence of dark matter and dark energy across cosmic time. Meanwhile, the Nancy Grace Roman Space Telescope and Euclid will sweep the heavens from orbit, measuring the subtle bending of light caused by invisible matter. These surveys may indirectly confirm whether the impossible particle is part of the dark matter puzzle, sculpting the universe with an unseen hand. But science does not rely only on giants. In quiet laboratories, tabletop experiments probe the vacuum with extraordinary delicacy, Precision atomic clocks measure the tiniest shifts in energy levels, sensitive enough to reveal the tug of unknown forces. Experiments with the Casimir effect, where metal plates are drawn together by quantum fluctuations, test whether new particles alter the vacuum's energy. Even Bose-Einstein condensates, clouds of atoms chilled to near absolute zero, are used as analogues to simulate the behavior of black hole horizons and quantum fields. In these humble experiments, the impossible particle may reveal itself not with a roar, but with a whisper. Supercomputers, to play their role, weaving simulations that stretch from quark interactions to galaxy formation. They model how anomalies like sterile neutrinos would shape the early universe, how supersymmetry would alter particle interactions, how a fifth force would change atomic structure. Each calculation is a map of the possible, testing whether the impossible particle can be reconciled with the cosmos we observe together. These tools form a tapestry of pursuit. Colliders recreate the violence of creation. Neutrino detectors listen to the silence of the void. Telescopes trace the architecture of galaxies. Clocks and condensates measure the hum of the quantum vacuum. Every machine is a question carved into metal and magnet. Does the universe hide a particle that should not exist? And yet, the search is not only technological, it is philosophical. For every experiment that confirms the standard model, another whispers of cracks. For every anomaly explained away, another emerges from the noise. The frontier is unsettled, and humanity stands in the tension between confirmation and discovery. What makes this pursuit extraordinary is not only the scale of its instruments, but the stakes of its answer. To find the impossible particle would mean rewriting the laws of physics. It would redefine matter, forces, perhaps even space-time itself. To fail to find it would mean something stranger still, that reality has teased us with illusions, that anomalies may be mirages woven into the fabric of measurement. Either outcome carries weight, either the world is deeper than we imagine, or more deceptive than we can bear. The machines remain vigilant. The LHC collides. Super Kamiokande waits. Muon G2 spins. Telescopes stare into the dark. Supercomputers churn their calculations. The hunt continues, across continents, beneath mountains, under ice, and in orbit above the Earth. Humanity has cast its net as wide as it can, stretching from the quantum to the cosmic, in hope of capturing one truth. Perhaps tomorrow, the impossible particle will reveal itself, a signal too strong to deny. Perhaps decades will pass before the whisper grows clear. Or perhaps it will never be caught at all, lingering forever at the threshold of possibility. But science endures, because the pursuit itself reshapes knowledge, turning absence into meaning, turning silence into discovery. The impossible particle remains hidden, but the tools of science grow sharper with every passing year, and in their watchful gaze, humanity continues its most daring act, to ask the universe questions it has not yet decided to answer. In the stillness of night, when the stars burn like ancient embers, and the sky stretches as an infinite cathedral, humanity lifts its gaze and wonders. Every star, every galaxy, every particle dancing in silence, all appear as parts of a grand design. Physics, at its heart, has always sought to describe that design with precision, to carve equations into the void that explain why something exists rather than nothing. Yet, at the edge of our most successful theory, a shadow lingers. A contradiction, a whisper of something that should not be. The impossible particle, it is more than a symbol of science's uncertainty. It is a mirror held to the human condition itself. For just as we are born with questions that never find answers, the universe too seems to contain riddles it refuses to resolve. When physicists speak of anomalies, sterile neutrinos, deviations, hidden bosons, they do not merely discuss numbers on a graph. They are speaking of cracks in the foundation of reality. If those cracks widen, the Standard Model, one of the most successful constructions of the human mind, could collapse. What remains would not be chaos, but something deeper, a truer structure waiting to be uncovered. But there is another possibility, that the anomalies fade, that the particle vanishes into error, noise, or misinterpretation. In that case, what would be revealed is not a new universe, but a lesson about our own limits. Perhaps nature does not bend to our expectations. Perhaps the act of searching itself carries more meaning than the discovery. The paradox is haunting. Whether the impossible particle exists or not, its shadow reshapes our understanding. If it exists, reality is far richer than we imagined. If it does not, then reality is more resistant to imagination than we dared to believe. In both cases, humanity is left transformed. For millennia, the cosmos has been a dialogue between silence and inquiry. Ancient philosophers argued over the void, questioning whether nothing could exist. Newton gave space a stage. Einstein gave space-time a fabric. Quantum mechanics filled the vacuum with restless fluctuations, and now the impossible particle stands as the latest verse in that ongoing dialogue, the question whispered back by the universe when we ask too much. At the heart of this mystery lies a profound tension. Science is built on symmetry, elegance, and order, but the impossible particle suggests asymmetry, disruption, imperfection. Like a cathedral with one stone out of place, it challenges the entire structure. Perhaps this is nature's way of reminding us that perfection is not reality's goal, that the universe is not a flawless equation, but a living story, unfolding in layers we cannot yet see, and there is a deeper, more personal reflection. Every human life is itself a kind of anomaly, fragile, improbable, existing against staggering odds. To live is to be, in a sense, a particle that should not exist. From the perspective of cosmic time, consciousness itself is a violation, a brief flare of awareness in a universe largely indifferent to thought. Perhaps this is why we are drawn so intensely to the impossible particle. It is not only physics we see in its shadow, it is ourselves. Consider what it means if sterile neutrinos exist, carrying with them the secret of dark matter. Then most of the universe is not only invisible, but fundamentally strange, built of matter that refuses to touch us. Consider if the Moyne anomaly persists, forcing open a door to new forces or supersymmetric partners. Then reality itself is layered like a hidden symphony, with harmonies we have never heard. Consider if X17 is real, a messenger of a fifth force. Then the four pillars of physics, ancient and unchallenged, stand incomplete. Each possibility is unsettling. Each carries consequences that ripple through cosmology, particle physics, and philosophy. Yet the unsettling is also the beautiful. It is precisely in the breaking of expectations that progress emerges. Physics has always advanced by confronting impossibilities: the atom that should not split, the photon that should not behave as both wave and particle, the black hole that Einstein once thought nature would forbid. Every time, the universe proved stranger, yet more profound, than belief. Perhaps the impossible particle is simply the next step in this tradition, or perhaps it is something else entirely. Perhaps it is not a doorway to a new theory, but a reminder that the quest is infinite, that for every particle we confirm, another will appear beyond reach, teasing us with mystery. In this view, the impossible particle is not an object, but a role, a shifting emblem of the frontier, always retreating as we advance. There is also the haunting possibility of silence, that after decades of searching, after colliders and detectors and telescopes, no confirmation will arrive, that the anomalies dissolve, one by one, into statistical noise. What then would the search have been wasted? Or would we discover that meaning lies not in answers, but in the act of questioning? Just as a horizon exists not to be reached, but to remind us of the vastness beyond, perhaps the impossible particle exists only as a horizon of thought. In this the story closes not in despair, but in reverence. The universe is not obligated to explain itself. Its mysteries are not failures of science, but its lifeblood. To stand before the unknown and admit uncertainty is not weakness. It is the essence of discovery. The stars burn, galaxies drift, space-time bends, and beneath it all, particles dance in silence. Some are known, others remain hidden. Among them may be the impossible particle, the one that should not exist. Whether it is found tomorrow, in a century, or never at all, it has already changed us. It has forced us to confront the fragility of our knowledge, the daring of our imagination, and the humility required to face the cosmos. In the end, the impossible particle is not a contradiction. It is an invitation to keep searching, to keep questioning, to keep gazing into the cathedral of the universe and listening for echoes in the silence. And so, the story rests with a final image, a night sky above a quiet earth. The stars seem eternal, yet they too are transient. The galaxies stretch beyond reach, yet their light reaches us still. Beneath it all, particles flicker in and out of being, carrying secrets too deep to hold. Somewhere in that silence, the particle that should not exist may be waiting, not to undo the universe, but to remind us that reality is greater than certainty, and that the greatest discoveries begin not with answers, but with questions.